Have you ever stopped to think about that invisible force that powers pretty much everything in our world? I mean, from the phone in your pocket to the lights in your home, it's all thanks to one single fundamental concept: electric current. And today, we're going to pull back the curtain and see exactly how it works.
So let me ask you this. What on earth could a huge, chaotic bolt of lightning and the tiny controlled charger for your laptop possibly have in common? Well, the simple answer is they're both electric current. But that simple answer, yeah, it hides a story that is way more fascinating and complex than you might think. Let's dive in.
Okay, so here's our game plan. We're going to break this down into 5 parts. First, we'll define what current really is. Then, we'll find out what makes it move. After that, we'll unravel a 200-year-old mystery. Then, we'll learn how to measure it. And finally, see how it all comes together in our everyday lives.
All right, first things first. To really get a grip on how current works, we need a solid definition. Because, trust me, it's a lot more than just moving electricity.
Now, the most important word on this slide is net. You see, inside any copper wire, electrons are constantly zipping around, just randomly bumping into each other. But that's not current. Current only happens when there's an overall directed movement of charge in one direction, a net flow. Think about it. If you have the same number of charges moving left as you do moving right, the net flow is 0. No current. So, just picture a simple circuit, with a battery and a light bulb. If the switch is open, the path is broken. There's no complete closed loop for those charges to travel around, so no light. But the second you close that switch, you complete the circuit, and boom, you get a flow. But that still leaves a really big question. Where does the push come from?
Exactly. A closed loop is critical. We get that. But something has to actually get those charges up and moving. What is the engine driving this whole thing?
And that push has a name: voltage. Or, if you want to be a bit more technical, potential difference. The absolute best way to think about it is like water pressure in a pipe. You can have a pipe that's totally full of water, but it's not going anywhere unless there's a pressure difference to make it flow. Voltage is that electrical pressure. It sets up an electric field that shoves the electrons along, forcing them to move from a place of high energy to a place of low energy. Of course, that push only works if the charges can actually move. That's where conductors come in. In materials like copper, the outermost electrons are kind of loose, so they can be pushed along really easily. But in insulators, like the plastic around a wire, the electrons are held on super tight. They don't want to move. And that's exactly why our wires are made of copper on the inside, but coated in plastic on the outside, to let the current flow where we want it and stop it from going where we don't.
Okay, now we're getting to one of my favorite parts of this story. It's a little confusing, but totally fascinating. For over 100 years, scientists had the direction of current completely backward. And for some very practical reasons, we've just stuck with their mistake ever since.
It sounds like it should be a simple question, right? But the answer really depends on a key detail. Are you asking about what we've all agreed to say, or what's actually happening?
And this is where it gets really interesting. Way back in the 1700s, Benjamin Franklin, long before anyone even knew what an electron was, he just took a guess. He figured electricity was some kind of positive fluid that flowed from a positive point to a negative one. Made sense at the time. But then, over a century later, J.J. Thomson discovers the electron, and he proves that in a metal wire, it's actually these tiny, negatively charged electrons that are doing the moving, and they flow from the negative terminal to the positive one, the exact opposite.
So here's the kicker. Even though we know for a fact that it's the electrons doing the moving, all of our circuit diagrams, all of our equations, all of our standards, they're still based on Ben Franklin's original guess. We call it conventional current, the idea that positive charge flows from positive to negative. What's actually happening is electron flow in the opposite direction. I know, it sounds a little crazy, but as long as everyone sticks to the same convention, all the math works out just fine.
Speaking of math, let's talk numbers. How do we actually measure how much current is flowing through a wire? How do we quantify it? Well, the unit we use for current is the amp, usually just called an amp. And what it means is actually pretty simple. 1 amp is just 1 coulomb of charge flowing past a certain point every single second. The formula looks clean and simple too. Current, which we write as I, is just the amount of charge, Q, divided by the time it took to pass, T. But what is a coulomb of charge? Get ready for this. To have a current of just 1 amp, you need this many electrons to flow past a single point in that wire every single second.
That's over 6 quintillion electrons. It's a number so huge it's almost impossible to wrap your head around, and it gives you a real sense of the incredible scale we're working with here. Okay, let's make this a little more practical. We can just flip that formula around to calculate the total amount of charge. So let's say we have a 2.5 amp current and it flows for 3.5 minutes. Well, first things first, we need to get our units right. So we convert 3.5 minutes into seconds. That's 210 seconds. Then it's just simple multiplication. 2.5 amps times 210 seconds. And that gives us a total of 525 coulombs of charge that went through that circuit. Easy as that.
So we can now define current, we can measure it, we know what makes it go. Let's bring it all back into the real world. How does this science actually power our technology? And just as importantly, how do we keep it safe?
Current basically comes in two main flavors. You've got direct current, or DC. That's what you get from a battery. The electrons just flow steadily in one direction. Nice and simple. Then you have alternating current, or AC, which is what comes out of your wall sockets. With AC, the electrons are actually flowing back and forth, reversing direction dozens of times a second. It turns out AC is way more efficient for sending power over long distances, which is why our entire power grid is built on it.
The whole reason current is so useful to us is because it creates these predictable physical effects. You've got the heating effect. That's just the friction of all those electrons moving, and it's how your toaster works. Then there's the magnetic effect. Anytime you have a current, you have a magnetic field, and that's the magic behind every single electric motor. And finally, the chemical effect, where current can trigger chemical reactions, which lets us do cool things like coating one metal with another. But of course, too much current is a really bad thing. If that flow of electrons gets too high, your wires can overheat and start a fire. And that's where fuses and circuit breakers come in. They are basically designed to be intentional weak points in the circuit. If the current gets dangerously high, a little wire inside a fuse melts or a switch inside a breaker trips, and it instantly breaks the circuit and stops the flow. They're lifesavers.
This quote really brings it all back home, doesn't it? The real power isn't in the random, chaotic motion of a few electrons. The power is unlocked when we get trillions and trillions of them to move together in one single directed flow. So let's do a super quick recap of the most important things to remember. 1. Current isn't just any flow, it's the net flow of charge. 2. Voltage is the push that gets it all going. 3. We use a historical convention for current's direction that's actually the opposite of how electrons move. 4. The scale is just mind-blowing. An amp is a ridiculous number of electrons. And 5. Current comes in AC and DC flavors, and we use things like fuses to control it. We've spent this whole time talking about what current is and what makes it flow. But here's a thought. Even the best wire in the world pushes back against that flow, at least a little bit. So what happens when you try to slow it down, or even stop it? Well, that's a whole other story, and it's a story all about resistance.